the mechanical properties of organic semiconductors. So the ultimate goal of this research is to make materials like ethylene. So this is ethylene, and then we get polyethylene. We can make these flexible plastic bags that are flexible and stretchable. The ultimate goal is to make the mechanical properties, or take the mechanical properties of something like polyethylene and make polyacetylene, or things like polyacetylene that are conductive or semiconducting. And we know they're conducting or semiconducting based on this alternating single and double bond arrangement. So what happens here is, as you add these p orbitals together, they can delocalize electrons and behave a little bit like molecular wires. So it's possible to transport charge in these materials. However, once you create this material, it becomes stiff and brittle. So the idea is, can we take materials with electronic properties like polyacetylene and give them the mechanical properties of something like polyethylene? And can we do even better than polyethylene? Can we make them truly like organic in the sense that connotes biological tissue, like the ability to self-heal and be tough and be sensitive to multiple modes of stimulus from the environment? The problem is, however, that as you look into the microstructure of these materials under strain, you can see that they're cracked and brittle. So this is an atomic force microscope image of not this material, but a similar material under 20% tensile strain. So why do we care about these conjugated materials? Well, organic light emitting devices are examples of commercial devices made from organic semiconductors. They don't happen to be semiconducting polymers. They're actually semiconducting small molecules, but the principles are the same. So solar cells in the research lab made from these materials are now, there was a recent report of more than 17% efficiency. So that's really almost competitive with commercial silicon modules. Now, of course, silicon modules are made routinely and on a very large scale, and we're quite far actually from making organic solar cells that quite achieve those numbers on a large scale. But at least there's some hope here. And the charge transport properties can actually be better than amorphous silicon. So this is an image from Frederick Krebs' group at the Danish Technical University, where they took these solar cells and they deployed them in rural Africa as part of the Lighting Africa initiative. Now that is to give students the chance to read at night after the sun goes down, to avoid having to burn unsustainable biomass and kerosene and so forth. But at the end of this field study, the researchers figured out that mechanical failure mechanisms were dominant during the field test. Now this is significant because you figure when you put organics out into the environment, they all kind of thermodynamically want to oxidize, become CO2 and so forth. So in fact, our bodies, if we didn't dissipate energy and self-repair and so on, thermodynamically, I would prefer to be CO2. I'm glad that I am an energy dissipating system, so that doesn't really happen, and that we can maintain homeostasis. But anyway, so we would expect that would be the case here, but it's not. Mechanical failure mechanisms are actually dominant when you put these things out in portable environments. And then the National Science Foundation and Office of Navy Research, around the same time that I started my job here, issued this workshop report that said that how do these cells fail mechanically? Do they fail at interfaces, or do they fail within the device stack? So this is kind of the proximate goal of the research. And the longer term research goal is to enable something like this. Now this is Mr. Data from Star Trek: The Next Generation, which I grew up watching and was inspired by. And actually when the NIH director's blog actually wrote a little bit about my research, and I told the reporter that I was interested in Star Trek and inspired by Mr. Data. My sister, before I had Twitter, tweeted out the story to her followers and tagged Brent Spiner, and then he retweeted it to 1.5 or 4, many millions of followers. That was the happiest day of my career. But again, the problem here is that if Mr. Data's skin were made of polyacetylene or materials that were not made to be stretchable and tough, again, you would have this fracture. So what we want to do is to endow these materials with mechanical softness and toughness, or hardness, in fact, just not brittleness, not junk mechanical behavior. We want to engineer the mechanical behavior. Capacity for self-repair, biodegradability, sensitivity to multiple modes of stimulus, and actuation for tactile response. And that's something that hopefully later on in the quarter I'll be able to tell you a little bit more about if you're interested. Okay, now the mechanical properties of polymers have been studied for a long time, so why not just take everything that's known about the mechanical properties, polystyrene, polyethylene, polypropylene, and just apply those on a one-to-one basis to semiconducting polymers. And the reason that's not possible, or the reason that it's difficult to do that, is because of the real complexity of these semiconducting polymers. So I showed you polyacetylene before. This is called PTB7. This is much better than polyacetylene because you can cast it from solution. But it has the same motif, alternating double, or double single, double single, double single, double single bonds across the entire structure. Now this is a really huge monomer residue, right? Like this looks like it looks like an anti-cancer drug, basically. So you're basically taking these huge monomer residues and polymerizing them together. Whereas we've got little old polystyrene here that's relatively easy to deal with. So what do we have? We have these alkyl side chains. The alkyl side chains serve to solubilize the material. How do they do that? So because this chain is rigid and these chains are floppy, there's an entropic benefit in solubilizing a material that has these side chains on it because they can occupy lots of different conformational space. So we have these rigid backbones, whereas the backbone here is flexible. We have low degrees of polymerization, and this is a result of the synthetic procedure that you need to make these materials. Also, the higher your degree of polymerization, the less soluble these materials tend to get. Why do you want them to be soluble? Because you want to be able to print them like newspaper. You have large monomer residues, small quantities available, maybe 200 milligrams is a good amount. Yep. So this particular one, some of them are soluble in water. This particular one is not soluble in water. This is soluble in chlorobenzene or tetrahydrofuran or something like that. Yep.
If you want to be soluble, like you could print it, wouldn't it dry off afterwards and become like solidified and
So the question is, if you want it to be soluble, wouldn't it dry out? And yes, you want it to dry out. You want to be able to process this like paint. You can make this in thin films only in general. So you're not going to find a big block of this material just because you can't melt process it. It's quite difficult to manage. Now, if you look at the microstructure and morphology, so this is this is nanostructure, even molecular packing structure. We have the range of microstructures available. We can have these side chains that interdigitate on the nanoscale. You can have non-spherulitic morphology, so these spherulites, kind of these three-dimensional snowflakes that occur in most polymers. They don't really occur here. You could have intercalation of small molecules, like small molecule additives, which you might need in between the side chains, which can complicate your analysis. You generally have a weak glass transition signal by calorimetry, and they can be challenging to model, although I'll tell you a little bit about some of the modeling efforts that we've made. Critically, compared to polystyrene, these materials must retain their charge mobility when deformed. So this is a tensile test of this material. This is poly-3-hexylthiophene, and we've plotted the stress-strain curves as a function of molecular weight. Now, as you increase the molecular weight, you're increasing the number of entanglements that you can have between chains, so that's where they literally entangle. And as a result, you increase the toughness, so the energy density prior to fracture. These are the results of a molecular dynamics simulation that more or less tell you the same thing. That is, you increase the molecular weight from 15 to 80 kilograms per mole, you have a factor of about 6 more entanglements in the high molecular weight version, and you can see that these chains are much more entangled and stay together. This work was done by Daniel Rodriguez, who was a PhD student who now works at Cymer ASML. He was also an undergraduate and a master's degree student in my group. Actually, a lot of this work that I'm going to show you is the result of undergraduate involvement in research, so I'd encourage all of you to seek undergraduate research options while you're at UCSD. Okay, now that is a property that we're quite familiar with. So molecular weight is kind of a tool that we use in the polymer engineering community to improve the mechanical properties. What about a molecular structural parameter? So this is the side chain. Again, this confers solubility to the material. And as you increase the length of the side chain, so as you increase n, and we plot the tensile modulus versus the side chain length, we have this steep drop off between C6 and C7. Now is that something magical about C7, about 7 carbons long? Not necessarily. It's really where we have the thermostat set in the lab. And the reason is the glass transition temperature of these materials is above room temperature, so these are glassy, they're stiff at room temperature, whereas these ones are rubbery. Sometimes you'll see C6 have a different TGs depending on what paper you look at, but it's around the borderline. In this particular case, it tended to be glassy at the temperature at which we did the experiment. So if you look at, don't worry about exactly what these numbers stand for, but just look at the color code here. So this is poly-3-hexylthiophene, this is poly-3-octylthiophene, so 2 carbon atoms longer in the side chain, and we have favorable charge transport properties. So these are the mobilities of holes in transistors, and this is the efficiency in a stretchable solar cell. So it's 2% efficiency, it's not 20% efficiency, but this is an all rubber semiconductor device. Poly-3-octylthiophene has kind of the reverse case, where the electronic properties are not so good, but the thermal and mechanical properties are favorable, so good deformability. If you look at number 7, it kind of fulfills lots of these criteria. So just by tuning these little parameters, just this 1 carbon addition to the side chain, we can actually enable some applications that we couldn't before. So this is a solar cell that kind of looks like R2-D2. You can take a solar cell and stretch it across 2 dimensions and bond it to a hemispherical surface, which might otherwise crack or wrinkle a surface. So why do you need stretchability? Why not just flexibility? Well, imagine a basketball, then a piece of paper, and trying to get the piece of paper to bond without conforming, or to bond conformally without cracking or wrinkling. You can't really do it, but you can if the material is stretchable. This is this video up in the top right is a wearable solar cell that my student could bend to about a 200 micron radius of curvature. He did this like 1,000 times, and then he put it on his wrist and powered up a watch. So he just took the battery out, and it runs. This is unencapsulated in outdoor sunlight outside the SME building, and this says 1201, and it says 1201 and not 12, so that you know it's been working for at least 1 minute. We have low standards in academic research in terms of device survivability, but we're trying to improve it. That's kind of the point of this project. This here is an all rubber solar cell. So this is the substrate, the encapsulant, the anode, the cathode, the charge absorbing layer are all low glass transition temperature elastomers. This work was done by Tim O'Connor, who is a grad student who also happens to work at Cymer ASML. Now, given the importance of the glass transition temperature in predicting the mechanical properties, you would expect them to be pretty easy to measure. But the problem is these materials are so rigid, and you already have all of this heat capacity tied up in these side chains, that when you look at the calorimetry data, so you add heat to the system as a function of temperature, and what you're looking for here is a change in heat capacity. So a change in heat capacity corresponds to the glass transition. Now these lines are all relatively flat, and we know that the glass transition occurs around here. It's pretty hard actually to calculate it. So we wanted to come up with an easier method that would give us a really sharp signal. So the question was, where's the TG? And my students had this hypothesis that it can be measured by the onset of aggregation by UV vis, ultraviolet visible spectroscopy. Now, what is the onset of aggregation? Who cares about that? Well, a conjugated polymer will pi stack. So these pi orbitals, they'll stack up and they'll almost they'll form a new type of absorber in the solid state. So these little crystallites of the conjugated polymer of the semiconducting polymer will absorb differently. And if we can measure the temperature at which these crystallites form, that means that the amorphous chains have enough energy to form these crystallites, and we hypothesize that that would be equivalent to the glass transition temperature. So the idea was to use a hot plate, and you bring your sample to a certain temperature on a hot plate and you measure the UV vis, and you calculate something called the deviation metric. And my student came up with this, which is the sum of the squares of the differences in intensity of absorption from some reference temperature to some temperature of interest. Nobody here knows what I just said. So here's a picture, and I would not have understood it just based on this. Basically, what you do is you measure these UV vis spectra and you find where the deviation is. And as you integrate all of these spectra and you square the differences, this is where these crystallites absorb. This is where they're aggregates. Before they're crystallites, they're aggregates. These are where these aggregates and then later crystallites absorb, right here. And actually, one time we submitted a paper where we did this analysis, and one of the reviewers said, all your UV vis plots look the same. Well, you don't need to include them in the paper. Well, you kind of do, because this is where literally all the data is, this one little spot. And if you crunch the numbers and you plot the deviation metric, it turns out, a huge change right here in the deviation metric. So our hypothesis says that this is the glass transition temperature. So how well did we do? Turns out that, that our measurements can actually be verified using, or supported using, atomistic molecular dynamics simulations. So, as you heat the material around, the density increases around the glass transition temperature, and if you quench the material from the melt, so you cool it slowly from the melt, you get this intersection of these tangent lines, which also correspond to the glass transition temperature. So these are the results in the black bars here from the UV vis data from our method, and then these dots here are the values from the literature. So we do pretty well. Now, it doesn't work for all of the materials. It tends to work only for the materials that stack this way, where the flat part of the molecule is stacking up. And it doesn't work if they stack this way, because the molecules can't add up their wave functions in such a way as to produce this additional absorption. Yeah, there's a question here.
So there's like a line that deviates from the nice curve on your PDT,
So a line that deviates from the curve.
Yeah, the one going 4, 3, 2, 1. Yeah, that one.
This line.
What is that supposed to be?
So these little transitions, I would have to look at the video of the simulation to tell you exactly what they correspond to. They could be artifacts. What we're really looking for is this abrupt change in slope of the density. And that would correspond to the glass transition temperature. Okay, so one polymer alone doesn't give you a solar cell. You need more than one material. You need the N-type material and the P-type material. Most of the materials that I've shown are P-type materials. So this is a P-type. It donates an electron to this Buckminster-Fullerene molecule that's functionalized with this junk here. And what's that junk there for? Again, it's to increase the entropy of the solubilized state. These are the highest occupied molecular orbitals and lowest unoccupied molecular orbitals that correspond to the roughly the valence band and the conduction band in organic media. This is the architecture of a device where we have the mixed layer of these two materials, and they could be two polymers, they could be any of the polymers that we've talked about, as long as you have the right offset in molecular orbitals. And this is a plot of the current versus voltage, and I think I showed you a plot like this earlier on in the class. So basically what you're looking for is this short circuit current density to be as deep as possible, this open circuit voltage to be as far out as possible, and for this line to be as square as possible in the fourth quadrant of the UV-Vis plot. So one of the things that we did was kind of a combinatorial screening method where we knew that polythiophene, this poly-3-hexylthiophene, was not necessarily the future of organic electronic materials or organic solar cells. So we looked at this kind of brute force library of materials. So these are one type of conjugated unit and another type. And what we did is took a cross product of each one of these paired up with each one of these. And these were all made by Frederick Krebs group at the Danish Technical University, and we did the mechanical measurements. So where it was possible to make these materials and do the measurements, we have data. In all the white space here, something wrong, something bad happened. Like the material couldn't be made, it wouldn't make a solar cell, we couldn't do the measurement because it was even too brittle sometimes. So this is the tensile modulus, and the lower the tensile modulus, the greener, that is, the better we're saying it is. Now that's because if you have a softer material, lower tensile modulus, it might tend to give you less interfacial stress with other layers in the device, and the device might survive easier. This is the crack onset strain, which is kind of like the equivalent of the strain at fracture, except that we're doing these on silicone rubber substrates because the materials are so thin. So what you do is you stretch it out. As soon as it cracks, you mark that down in your notebook. So the higher the number here, 68% strain, that's pretty good for a semiconducting material. Try doing that to a silicon chip. 57, also pretty good. So then my student came up with this kind of arbitrary way to combine the efficiency of these materials times the inverse of the elastic modulus times the crack onset strain, and gave it this performance parameter, capital psi, or capital C. C sounds like C, so we're going to say psi. And then normalized it to the performance parameter for P3HT. Now this is the fruit fly material to which you compare pretty much every other material in the field. So it turns out if you calculate this parameter, this merit factor, some of these materials are actually predicted to be better than P3HT if you combine knowledge of the predicted thermomechanical stability with the power conversion efficiency that were measured by the Danish group in a solar cell. This work was done by Suchil Savagatrup, who got a postdoc at MIT and is now on the faculty job market. So what are the design rules here? So this brute force experiment is only really valuable insofar as we can figure out what are some characteristics that we can apply to other materials in the future. So isolated rings tend to give you more flexibility than fused rings, and also branched side chains tend to give you more deformability than linear side chains. Yep.
In the title it says there's 51 polymers. Are you showing only a select number?
Yeah, the 51 polymers were the ones that it were possible to actually synthesize. Some of these materials, because of some idiosyncrasies of the chemistry, we didn't get material. Yep.
So the merit factor chart, I noticed, doesn't have the same number of blocks as the other two charts.
Yep. Okay, so the merit factor chart, we had to be able to measure the modulus and the crack onset strain and a solar cell. So we only included the data here for the materials that we could measure all three parameters.
Okay.
Yep.
So it looked like A5D7 block was the best?
A5D7 was the hero of this experiment. Yep. So, so we did look at some of these materials in more detail. We did not actually look at A5D7 because nobody knew anything about it. Which is kind of when you go on one of these fishing expeditions, you hope to be able to find something that's really good. But we had very limited quantities of it. So we looked at some other materials, and not necessarily because they were particularly well performing, but because there were hundreds of papers about them and we could compare our results to them. And those were these relatively modest performing materials. And those we chose because a lot is known about them, and also because they form this wide range of microstructures. So from semicrystalline, PDTSTPD, it took me a long time to practice saying that, PDTSTPD, anyway. PTB7 and TQ1 are semicrystalline, intermediate, and amorphous. So my student Sam Root, who's now a postdoc at Harvard, actually working for my old PhD advisor as a postdoc, did these molecular dynamics simulations in which he calculated the properties of 60 chains of 12 repeat units each in both the neat film, so that is the pure film of the polymer, and the BHJ, which is the bulk heterojunction, which is the polymer mixed with the fullerene as the electron acceptor for a solar cell. Yep.
So with the previous slide, how do you guys come up with these equations and the like to predict?
Seriously.
So how do we come up with the equations? This here is actually quite an arbitrarily decided equation. We had an idea that the efficiency and the crack onset strain, the better they are, the better. The higher they are, the better. We know that that if you have a really stiff material, it tends to debond from other layers in the device stack. It tends to correlate with poor survivability, so we use the inverse. And we gave them all coefficients of 1 to 1 to 1, completely arbitrarily. But you got to start somewhere. For the merit factor, for the UV-Vis experiment, we were interested in collapsing those UV-Vis parameters down to something that you could plot that would give you a big difference when you're comparing very, very similar spectra. And so the question is, so sometimes you come up with equations by different levels of theory. So you can have a semi-empirical model. You can have a model that is derived from really deep physical principles and build it up and build it up, or you can guess and compare different models, and then the ones that describe the data are the ones that you hope can describe future data. Now, the mother of all coming up with models is these computational studies, right? Because you have to input the van der Waals energies and the torsional energies and the Coulombic attractions and everything for every single atom in this thing. And then you give it to the San Diego Supercomputer Center, which is like half a mile away, and you program. Well, it's near the REMAC, and you program how it's going to treat these systems, and then it spits out your data. And then you can take the data and you can plot it, or you can visualize it using rendering software. You can plot various quantities, and you can test hypotheses using it. So you can imagine that there are lots of different ways of generating these solid films that give you different properties depending on how you process the film. So you can imagine a melt-quenched morphology. Now, melt-quenched means you take literally a melt of the material and you cool it down slowly, and you get a solid material that's quite dense and well entangled. you can imagine a self-aggregated morphology, which instead of melting it, you dissolve it. And you dissolve it, not only do you dissolve it, but you dissolve it in a bad solvent, where the polymer molecules shrivel up on themselves because they don't want to interact with the solvent. Then when you evaporate the solvent and you solidify the film, the polymer molecules are already balled up. They're already kind of aggregated. They form this low density film that's predicted, at least by these simulations, to have a low density of entanglements. Interestingly, we found, this is based on some work by Nick Jackson and as a postdoc in Mark Ratner's group at Northwestern University, where we found that we could bin these different structures into different conformational classes of polymer that depended on, well, they kind of sound like the name. So globule, toroidal, which is kind of like a spiral. We have folded structures, which is just maybe has one or two folds in it, and then these relatively extended structures, which are kind of like these linear. Now, each one of these polymer molecules could roughly be binned like this, and you can plot the number of each material, PDT, STPD, PTB7, and TQ1, that end up in each one of these types of structures. So no surprise here, the globular morphology had a high proportion of TQ1, and TQ1 was the amorphous material, and we knew from X-ray diffraction experiments in the literature that it's relatively disordered. This is an interesting experiment here. Well, this is an interesting finding from the computation. This is called a tangent correlation function. So stay with me for a second, because it took me a long time to figure out what this actually meant when my student was explaining it to me. Okay, so imagine that you have this polymer chain, and you can draw tangent unit vectors along each monomer in the chain. So the tangent correlation function is the dot product of the tangent vectors between some reference monomer and some monomer farther on down the line. Now, you would expect for a completely disordered mess of a polymer chain, like a random coil, like a globule, that you would have some correlation for the first few monomers, and then it would be pointed in whichever way. But imagine if you had some helicity to the material, where you count down some number of monomer residues and there's correlation, because now you can predict with some amount of accuracy the probability that you'll be pointed in the same direction as the first tangent unit vector. So in the case of a globular system, we expect an exponentially decaying tangent correlation function as you go along the chain. But we don't have that here. We have this oscillatory behavior, and the oscillations are the result of these helical or ribbon-like twists or ribbon-like bends in the chain, which is not something that had been explored before. Yep.
So by taking the dot product of two tangents, you're essentially trying to tell, I guess, which direction they're going in relation to each other?
Exactly.
What was the thought behind that? Were you trying to see where the dot product equals to zero, where they're pointing in the same direction, so it's oriented the same? What we
were trying to do is find another way to quantify the order in these structures. And this is a nice way to visualize this sort of repetitive orientation that we found. Yeah.
Assume all of the tangent vectors are unit vectors?
All the tangent vectors are unit vectors.
How can you have negative correlation? Does that mean it goes against what you would expect?
So the negative correlation, so it's not negative correlation. So the negative means it's pointed the other way. Yep. There's another question. Yep.
I was just going to ask, how did you, what method was taken to look at this and to measure the direction of each thing?
Yeah, that's a good question, and it's in this paper, and I can send it to you, but there's a lot involved in extracting this plot from the data. All right, so another thing we can do that's really cool from these simulations is to calculate the number of entanglements. So you can really zoom in a way that you never would be able to experimentally. So you can zoom in and you can find these individual kinks in the chains where the polymer molecules are entangled. So if you plot these primitive paths of the molecules and you see where they intersect, that corresponds to where there's an interior kink. So you can go around, you can actually calculate where they are. And we can see that in the melt-quenched morphology, we have the most interior kinks. And what that leads to is that in the melt-quenched, which is actually this morphology. Forget the word thermodynamic and kinetic. This is the melt quenched. This is the self-aggregated morphology. We can see that the materials actually behave relatively similar. So the way that you process the film is quite important, and perhaps even more important than the molecular structure, assuming that they all have similar solubility properties, which they don't. So the molecular structure is important, but the way in which you process the film, to a large extent, because of these nanoscale phenomena, really determine the properties that you get overall. So from the very tiny scale, we also looked at whole modules, and these modules were again made by Frederick Krebs' group in Denmark. And what we did is construct these solar cell torturing devices. So this is a twister. It's you can also reconfigure it into a bender, and you can get it to fail. And the goal is, after literally, I think we cycled like 30 cells, some total of like 1.5 million times. Some of these cells actually last more than 10,000 cycles of bending or torsion. And the goal is of this research to be able to calculate, or to really to calculate and predict where in the device stack the materials are going to break down. So this project was started by Alex Zaretsky, who founded a company, who had graduated from the group and licensed some of our technology, and founded the company Groltex, based down the street, actually, in Scripps Ranch. And Mickey Finn, who is a BS, MS student, and PhD student in the group, or now PhD student in the group, who finished out this project. Now, what's happening in the molecular scale when you cycle these polymers over and over in bending and stretching? So we see these UV vis plots again, and the idea is, can we analyze this and get some molecular information as to what's happening? So we 3D printed this starship-looking thing, and then my students stretched these materials again like 10,000 times, because we like 10,000, it's a good number. And then you plot the aggregate fraction, so the fraction of the chains that are in these pi stacked aggregates goes down as you keep cycling the material. So this is at 5% strain, 10,000 times, 10% strain, 10,000 times, 25% strain, 10,000 times. So as you stretch this material over and over again, you're pulling these aggregates apart. It's a little bit like taking the top of a tic-tac box and bending it over and over and over and over again, and you're changing the microstructure of the material, and eventually it will snap off. Yep.
So how are you guys coming up with these different error bars?
So there is a little bit, if I go into that, I'm not going to be able to finish on time. But we have, because I'm a professor, I cite everything. So so the error bars, different samples, different runs of the same sample, and then how do you calculate the aggregate fraction to begin with? You need a photophysical model to plug in the data to. So there's a lot going on here. Interestingly, the wrinkling wavelength, so if you stretch something and then you bring it back to, so we've got an elastic slab, then we've got our film on top, and we stretch it. And as we bring it back to equilibrium, since we've stretched the film, it now wrinkles. Now the wrinkling wavelength is actually related to the tensile modulus of the film. So as the wrinkling wavelength goes down, the tensile modulus is actually predicted to go down as well. So we're making this material, we're pulling the aggregates apart, we're making it softer. This work was done by Adam Prince, who's now a tenure track professor at University of Arizona in the Chemical and Environmental Engineering department. Yep.
Sorry for the number of questions.
That's fine.
Since it's related to the tensile modulus, is it also related to the Young's modulus?
So tensile modulus and Young's modulus are the same. All the forms of elastic modulus, so shear modulus, bulk modulus, Young's modulus, and the Poisson ratio are all interconvertible if for bulk unstructured materials, which these are not, especially after you stretch them, but in general they are. So it also becomes more brittle. So it becomes less stiff but also more brittle. It becomes a little bit like the soup skin on Campbell's tomato soup after you leave it out for a few minutes, and you get this soft skin that's also brittle on the top surface of the soup. Same kind of material here. And here's our little cartoon. So this is the as-cast material and then the fatigued material. So it becomes basically like the top of a Tic Tac box after you bend it over and over and over again. Now sometimes you can prevent cracking by encapsulating the material. So what happens when you stretch these materials to 50% strain on an elastic substrate, you get all these cracks. Our hypothesis was if you put another layer of elastomer on top, you can redistribute strain energy and suppress the formation of cracks, and that's indeed what we see. So these are some finite element models, sometimes called rainbow diagrams, which kind of show you that encapsulated films, if they have pre-existing defects in here, then they concentrate stress to concentrate strain to a lesser extent than those that are not encapsulated. So we don't always need to change the molecule, the molecular structure, or the microstructure. Sometimes just the device layout can actually give us what we need. Now, it's also possible, I've got to speed up because there's something I want to get to. It's also possible to extract information from the crack shapes. So they form, these ductile films form these diamond-shaped cracks. And it's possible, actually, and this work was done by Mohammed Al-Qadra, who was a BSMS student, now a PhD student at MIT, and Kristan Hilby, who's a current undergrad student graduating this year. So it's possible to take the growth rate of these diamond-shaped cracks and actually correlate them to properties that you would measure by these stress-strain curves. So for example, these diamond-shaped cracks for ductile films, as you elongate them, the more brittle they are, the longer they get compared to how wide they get. And if you plot the growth rate of the aspect ratio as a function of strain, and you take the log of that material, you get a straight line when you plot it against the fracture stress, which is pretty cool because we didn't even need to do a pull test on the material. We just needed a microscope and stretch the material. And we did it for a range of different organic semiconducting polymers here. Another thing we did was take a look at the flexibility and branching of the side chains. And this is some chemistry that you don't have to worry about. So there's a kind of a joke in this field that what takes the scientist 90% of the time to do when it's presented, that data is we kind of skip over it. But anyway, it takes a long time to synthesize these materials. But basically, we made this material with all these different side chains. And I want to get to another thing. So suffice it to say that if you have these ethylene oxide side chains, which are more flexible than these alkyl side chains, then the overall material tends to be less stiff and brittle and more deformable. Moreover, if you look at the field effect mobility in a transistor and the power conversion efficiency in a stretchable rubber solar cell, you can see that some of these materials, like this EO4, so EO4, 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 tend to give you the best of both worlds in deformability and charge transport properties. Another thing we did was to try to give the material not just this deformability, but also biodegradability. I'm going to take the question at the end. But also biodegradability. So this is a structure, we didn't make it. I put it in a grant proposal, but it turns out it was unmakeable. But I just want to highlight it because I have the sections here. The idea was to take this biodegradable segment, copolymerize it with this semiconducting segment, and then have these ethylene oxide side chains that confer flexibility. And then ideally be able to degrade this thing in the environment or even inside the body for an implantable type application. This is the structure that we actually made. So sometimes plans don't work, you need to redesign things. And the stress strain curves show you that you can indeed stretch them out a lot. This work was done by Fumitaka Sugiyama, who is a visiting scholar from Japanese synthetic rubber, JSR, in Japan, who was with us for 2 years. Here's the chemistry. Took 99% of the time, but only 2 seconds to talk about. Sorry about that, Fumitaka. And then the charge mobility and degradability. So this is the charge carrier mobility of the material as a function of the amount of biodegradability. So as you increase the amount of biodegradable stuff, you'd expect the charge mobility to tank. But if you have the right comonomers in here, you have these right comonomers, you can actually retain this charge carrier mobility. Now, if you plot the aggregation behavior, the order in the semiconducting regions actually increases, which is a good thing. And also, if you dissolve or hydrolyze the degradable segment and you compare and you look at this material, which is 75% of the biodegradable stuff, what's left over is the semiconducting stuff. And if you kind of squint your eyes, you can kind of see a percolated charge transport pathway here. So that was really encouraging. And the last slide I want to show you is we're not interested not just in the semiconducting part, but also the conducting materials, because those are what you make electrodes out of. So this is PDOT PSS. It's used as anti-static coatings. It's conductive. What we wanted to do is make this kind of bottle brush polymer, and then make the conductive part here. And the bottle brush polymer is really slippery and wiggly. It kind of looks like proteoglycans, which are like hyaluronic acid in the joints and stuff, to be really deformable. So again, here's the chemistry. Took all the time, and here's the material. And what we get, this is the business curve. You can make it really, really tough and stretchable by having this kind of cartilage sort of inspired block within the material. And this work was done by Laura Kaiser, who's a postdoc in the group who's deciding now between 5 faculty offers at research institutions. So with that, we look really at a range of material properties from molecular structure all the way to bulk structure and defects with some modeling and synthesis. And here's our chemical reviews article, which is available freely to the public through the American Chemical Society Editor's Choice Award. And this is my group, but I highlighted the specific contributions. This work was funded primarily by the Air Force Office of Scientific Research, with a lot of contribution from the NIH Director's New Innovator Award, particularly on the biodegradable materials. So with that, thank you for your attention. I'm pretty much out of time, but maybe I have time for like one quick question.